Hello everyone, and welcome back to our class in Artificial Intelligence and Finance. In this video we want to look at the application of neural networks in a very generic example that is frequently used in economics and finance, but that is scanning documents. Usually these documents only exist in paper form, and we have invoices, bank statements, printouts of static data, business cards, receipts, etc. And a scanned image cannot be searched in its native state. Thus, it is usually common to digitize printed text to enable electronic editing, searching, compact storage, and online display. And then for this, you need neural networks. The retrieved hidden text behind an image can also be fed directly into further machine processes. For example, automatically managing invoices, receipts, transactions. And you can imagine that this is usually the starting point, digitalization of these printed documents that decades and years ago were only available in printed form, but nowadays they can be digitized and used in a computer. Now, the technique behind this is usually called optical character recognition, OCR, and this is done by neural networks. This is one of the most basic applications of neural networks. One can also use them in asset pricing. I'll comment on that later on, but I think this is very instructive because you can easily see how the neural networks work. So on the following slides, we employ neural networks for the task of handwritten digit recognition, a classification problem with 10 classes, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. We have a handwritten note, and we want the neural network to be able to decide, is this a 1, is this a 5, or is it 0, for example. We start with the multi-layer perceptron. It doesn't make too much sense to use a single layer perceptron here if we can also use the multi-layer one. The principle is the same. And we will discuss some regularization techniques to prevent the model from overfitting. And we will also fit a convolutional neural network to the data. For the application, we now rely on the MNIST database that is provided within the Keras R package. And this database contains 60,000 training and 10,000 test examples of handwritten digits. And more details on this particular dataset can be accessed at this link here. So this is the MNIST database in Keras. Okay. So we employ the Keras R package for fitting the neural networks. This package provides an interface for the open source Python library, Keras, which in turn acts as an interface for Google's TensorFlow library. You might have heard TensorFlow, which is the library provided by Google on deep learning, machine learning. And the syntax in the R package is very, very similar to the Python syntax in the original library. And it's one of the leading high-level neural network APIs, and it has a focus on enabling fast experimentation, quite user-friendly, and it also allows the training of neural networks on both CPUs and GPUs without changing the codes. We need additional computation power here, and it also supports arbitrary network architectures, and it's quite appropriate for building essentially any deep learning model. That's why we are using this here, and also we are able to stay within R. Now, before we can start to work with the data, we have to install the Python, Keras, and TensorFlow backend first. This can mainly be done from within R, and during the process you might be asked which TensorFlow version you want to have installed. If you use default, this yields the CPU version, which we'll use here. But please note that installing Python Keras via the Keras R package seems not to work on the RStudio service. So if you are using RStudio, please use your own computer, and this doesn't work. So before executing the following lines of code, please also install Anaconda with the default settings from here. That's Anaconda. And then you install Keras, and this third line will also install Miniconda and several Python packages, Keras, NumPy, etc. So this is what we need in the back end in order to be able to fit our multi-layer perceptrons and our neural networks. Again, we start by importing the data. We load the library Keras, and then MNIST is dataset MNIST. This downloads the database, the object size divided by 100, no, actually 1 million. This is 219. This is the size in megabytes. So this is not really large, but it might be too much for, let's say, a regular notebook. Might be that the data, even this rather small data set, is even too large for a regular notebook. So this is why we are not using larger data samples here in this lecture. To have a look at the structure of MNIST, you can see it's a list of two. It's training, $training, that's one object, and $test. And you see it is now a very simple structure. Why is that? Well, the data basically is, these are just digitized images. It's not features like in the insurance risk premium data sample where we saw we have age, gender, etc. These are all images, and they are not saved as images, as JPEGs, obviously, but they are saved as digitized images. And how is this? For example, if we view MNIST, that's our data sample, and in the training dataset X1, the first observation, you can see this matrix. You can see a 28 by 28 grayscale image, and what you see is actually these are all numbers. If we zoom in here, you can see these are all numbers. And you can imagine what has been done. Actually, this is one of the images. Let me zoom out. And this actually looks like this. This is one example. I would guess this is supposed to be a 5. Someone wrote down a 5, and this is the digitized version of this. So if you check the image label, you can visualize it. And yes, we would guess that this is a 5. Actually, yes, it is. So if we look at the response, the output value for this observation, it's a 5. And hopefully later on our models are able to train on the training data and then be able, if it's fed this image, to be able to determine that this is supposed to be a 5. Okay. Now the data are stored in a 3-dimensional array. We have, if you take a look at this, as you can see this is the first dimension, 1, then the second one, and the third one. The first dimension is for the image. This is the first image, so we get a matrix in the remaining 2 dimensions, so 1 and 2. So actually all the data are stored in a 3-dimensional array, image by width and height. So actually, if we were to access 1, 3, 2, where's my cursor? Here it's my cursor. 1, we could get the first image, 3, line 3, and column 2, we would get this 0. So this is how the data is stored. Now, to be fed into a multi-layer perceptron, this matrix has to be flattened. That is, it needs to be transformed into a vector. And additionally, because as you can see, the data is stored in grayscales from 0 to 250, we need to transform the grayscale values between 0 and 255 to the range between 0 and 1. So xtrain is MNIST $train $x, ytrain is MNIST $train $y, and so on for the test data. We need to reshape the data, so xtrain and xtest are xtrain from before and xtest from before, and we reshape them by flattening it, and then we rescale this by dividing all the numbers by 255. If you divide everything by 255, this whole range from 0 to 255 is transformed to the interval from 0 to 1. That's in lines 10 and 11. And then the y data, These are integer vectors with obviously integers ranging from 0 to 9. So 0, 1, 2, 3, and so on and so on. And for training, we one-hot encode the two vectors into binary class matrices. So this is done via the Keras two categorical function. So you can see here the structure before transformation is 5, 0, 4, 1, 9, 2, 1, 3, 1, 4. These are the values. This was our first image. That was the 5. And if we do this to categorical, y train and 10, you can see this is now a matrix. And we now have categorical or binary variables that, for example, if we start with the 0, which is actually the first observation we have, the first binary variable. So is this a 0? No. 0. Is this a 0? Yes. 1. Is this a 0? No. 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 And we get 0, 1, 0, 0, 0, 0, etc. And this is why test in the same manner. Now next, in the next video, we are going to fit the multi-layer perceptron to this type of data.